In this lecture, we're going to look at number systems. We talked about how computers use not the decimal number system, but the binary number system because we represent numbers in computer hardware as electrical signals that are either on or off, or as magnetic signals with like the north or south pole. And so computers don't have a way to count to 10, they can only count up to 2, and so we use binary instead of decimal. So what we want to be able to do today is convert values between binary and decimal number systems. In order to understand how binary works, we actually have to take a step back and think about how our natural decimal number system works. And so this might seem sort of elementary because everybody kind of knows how to count in base 10, but I really want you to think about what these, how these numbers are represented, and specifically what place value means. So in the base 10 number system, every place, that is every digit, represents a power of 10, right? And so when we see a number like 67,231, the 6 actually represents 60,000, right? Because it's in the 10 to the 4th position. So think about these positions. The 1 is in the 10 to the 0 position, the 3 is in the 10 squared, or 10 to the 1st position, the 2 is in the 10 squared position, the 7 is in the 10 to the 3rd position, and the 6 is in the 10 to the 4th position. And what we're actually doing is adding up these values, which are multiplied by their place values. That's really important because the only real difference between number systems like binary and decimal and hexadecimal is the place value. Okay, so it's 10 in what we're used to. This is what changes in other number systems. So let's look at binary. In the base 2 number system, that place value, which was 10, is now 2. Okay, and so the places here, are 2 to the 0, which is still 1, just like 10 to the 0 was 1. But the second place isn't tens, it's not the tens place, it's the twos place. And the third digit isn't the hundreds place, it's the fours place. The next digit isn't the thousands place, it's the eights place. And this fifth digit isn't the 10,000ths place, it's the 16s place. Because we're multiplying by powers of 2, not powers of 10. Okay, so we're still doing everything else the same, right? This 1000, 1000 plus 100 plus 10 plus 1, it still produces this number. That addition is not any different, but what this number means isn't 10,111 anymore because the place values aren't powers of 10. Well, let's look at what this value actually does represent then. If it's not 10,111, what is it? Well, this first 1 isn't 10,000. It's not 1 times 10 to the 4th. It's 1 times 2 to the 4th. 2 to the 4th is 16. So this 10,000, this number that looks like 10,000, is actually just 16. Right? This number that looks like 100 is actually just 4. And when we add these numbers, we get the number 23. So even though this number looks like 10,111, if we're in the binary number system, you would actually read this as 23. This is the number 23. This is a little joke, and I'll leave it to you to figure it out. You can talk to with a neighbor if you don't get it. Okay, what if we want to go the other direction? We want to convert from from decimal to binary. Well, let's say we've got a decimal value, 41, and we want to write that as a binary number. What we want to do, we're going to do this in two different ways. We want to think in powers of 2. The first method is to go from biggest to smallest, and I would recommend until you get used to it that you kind of write down the powers of 2. So 2 to the 0 is 1, 2 to the 1st is 2, 2 squared is 4, 8, 16, 32. We'll stop at 64. Okay, 64 is 2 to the 6th. But we could keep going, 128, 256. And what we're trying to do is figure out, well, what kind of powers of 2, what digits of the powers of 2 does 41 have? Well, the largest power 2 that fits into 41, 64 is too big, 32. 32 fits into 41. One time, right? So we write a 1. This first 1 represents 32. How much is left when we get rid of 32, when we take that off? Well, we have 9 left that we have to account for. What's the next power of 2 that fits into 9? Well, 32 is too big, 16 is too big, 8. 8 fits into 9 one time, and so we put a 0 for the 16's place. So remember, this was the 32's place. This is the 16's place. There were no 16's. This is the 8's place. There's an 8. 1, 8. So we put in a 1. And that leaves us with 1 left over. 9 minus 8, there's 1 left over. Well, what's the next power of 2 that holds 1? Well, clearly 1 is 2 to the 0. So there are no 4's, no 2's, and a 1. And so this is our binary answer. At any point, pause this video and try to make sure that you understand before you continue. This is one way to look at binary numbers. There's another way that might be kind of better. If you can understand this second way, then you really understand how binary number systems work. The other way that we're going to talk about here is to go from smallest to largest. And the key to doing this is to realize that each binary digit is double the digit that comes after it when we move from left to right. So what I mean by that is the place values are multiples of 2. So the first place value is 1's, the second is 2's, the next is 4's, etc. So the only time we have a 1 in a binary digit is when the number that we're looking at divided by the place value is odd. So let's look at 41. And we're looking at the ones place. Well, 41 is odd, so there has to be a 1 left over. So we're going to go ahead and write a 1, because since 41 is odd, there has to be a 1. All the other digits are powers of 2, so that every other digit is going to be even, or is going to have an even value. And so the only way we get an odd value is if we have a 1 there. So we've accounted for 1. So we write that 1 down, and now we have 40 left. So we look at 40, and we're looking at the 2's place. Okay, 40 divided by 2 is 20. That means there are 20 2's that fit into 40. That's not an odd number, so there's not a leftover 2 here. Right? If we had a 1 here, there'd be like a leftover 2, and so this has to be a 0. Okay, there isn't a leftover 2. There are an even number of 2's. Okay, so now we move to the 4's place. We still haven't, we're still looking at 40 now. 40 divided by 4 is 10. That's an even number. That means there are an even number of 10's, and there's not a leftover 4. So we're going to write a 0 in the 4's place. Okay, and we haven't accounted for anything, so we're still looking at 40. Okay, we move to the 8's place. 40 divided by 8 is 5. Is that odd? Yes. So there's a leftover 8. So we need to account for that leftover 8 by putting a 1 in the 8's place. This is 1 8. It's a leftover 8. And so we've taken care of 8. There are 4 more 8's that are still left in here. So we write a 1 for the 8's place. We take off 8. That's 32. Is 30, now we move to the 16's place. Is 32 divided by 16 odd? Nope. So we write a 0. And we move to the 32's place. Okay, 32 divided by 32 is 1, which is odd, and that takes care of everything. And so we get 1, 0, 1, 0, 0, 1, just like we had before. And that's how we convert between decimal and binary numbers.